Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on August 1st, 2025, so just about 3 days ago. This paper tackles a major bottleneck in diffusion large language models, which generate text all at once instead of word by word, by letting them dynamically adjust their output length. The paper is titled, Beyond Fixed Variable Length Denoising for Diffusion Large Language Models. And as we'll see, this makes them not only more accurate, but also way more efficient. The new strategy, DAEDAL, uses the model's internal confidence signals to expand the generation space on the fly, without needing any retraining. Also, the authors shared their implementation on GitHub. If you check out the DAEDAL repository, you'll find everything you need to get started. This includes the setup instructions, all the evaluation scripts for their method, and even scripts to run the baseline comparisons, so you can really dig in yourself. Alright, so to really see the difference this makes, let's look at the first set of charts. These compare DAEDAL to a standard fixed-length denoising baseline, which is the regular way these models work. You can see for the baseline, in blue, you have to carefully tune the output length for each task to get good results, and making it too long can even hurt performance. DAL, the orange line, consistently outperforms the best-tuned baseline across different tests. The bottom chart then shows exactly why. The baseline is stuck, using one predefined length for every problem, but DAEDAL dynamically adapts, using a whole range of different lengths tailored to each specific question, which is just much more efficient. So how does the model know when the length isn't enough? Well, that's the core insight, and it's visualized in these heat maps for the GSM-8K and Math 500 benchmarks. They show the model's confidence in predicting an end-of-sequence token, which is a special marker that basically says, I'm done. The predominantly green color shows that when the given space is sufficient, the model is much more confident about finishing. When it's not sufficient, that confidence drops. This confidence gap is the key internal signal DAEDAL uses to expand the length. So this next figure shows exactly how that works in practice. The top diagram shows the standard method, called fixed-length denoising. The model gets a fixed number of blank or mask tokens and has to fill them in. The length never changes. Below that, you see the DAEDAL process. It has two clever stages. First, initial length adjustment uses that confidence signal to find a good starting length. Then, during generation, a process called iterative mask insertion finds low confidence spots, called expansion points, and injects more mask tokens right there, giving the model more room to think on the fly. And this table really quantifies the benefits of that two-stage process. It compares the standard fixed-length denoising baseline against DAEDAL on benchmarks like the GSM-8K reasoning task. Now, besides accuracy, it measures efficiency using the effective token ratio, which is the percentage of tokens used for the actual answer versus the total generated. For GSM-8K, DAEDAL not only beats the baseline's peak accuracy, but it does so with an effective token ratio of 73.5%, compared to the baseline's best of just 27.7%. This shows it's achieving better results while wasting far less computation. Building on that, this table shows an ablation study, which is where you test a system by taking parts away to see what each one does. We see that stage 1 alone, the initial length adjustment, already beats the best baseline. Stage 2, the iterative mask insertion, also helps significantly. But the full DAEDAL method, with both stages working together, achieves the highest accuracy, showing they are truly synergistic. So, in conclusion, DAEDAL effectively solves a fundamental bottleneck for diffusion large language models. By listening to the model's internal signals to dynamically adjust the output length, it achieves better performance with far greater computational efficiency. That's it for this episode.